Today we're going to be discussing attitude representations, and so we'll start with a little diagram here. Before we get super far into it, any quick questions about the things that we discussed in the last couple of lectures, a review of orbital mechanics? I did add one bit to the notes after we kind of hung up last time, in case you were curious. You might remember when I was going through the steps and showing how you can piece together the attitude matrix to get from the inertial frame all the way to the parafocal frame, I kind of left out the matrix math and said, well, it's going to be some ugly mess, and then showed you these equations without derivation. In case you're curious, this is the ugly mess. And if you study it for a second, you can see how the bottom right element has information about inclination. These two elements in blue have information about the, I just realized
we can't see anything.
Yep, that would probably help. Okay, bear with me here. There we go. Okay, sorry about that. So I mentioned that there was some ugly mess, and then this is the matrix that I was referring to that I didn't feel like writing out. But I think it is instructive to actually see it. And what you notice is that the top left 2 by 2 is very ugly. So S omega means sine of omega. I didn't have the wherewithal to go through and write that all out. This is too much. But you can see how the bottom right element has information about inclination. So if you do the arc cosine of the bottom right element, that gives you your inclination. And that's exactly what this equation here was saying in red. And then if you take a look at the right 2 elements here, which are circled in blue, they have information about inclination. But if you take if you divide these two, what you get is the tangent of little omega. And so you can do the arctangent of the division of those to recover little omega. And then similarly, with the 2 that are circled in yellow, you have information about big omega. And so you can use those to back out big omega. So I think that for folks that haven't seen this before, or for folks that are a bit rusty on orbital mechanics, I think hopefully it helps to actually see the matrix written out. So this is the ugly mess that I was referring to. But yeah, before we move on to attitude representations, any orbital mechanics questions, or we're good to move on, we think? All right, we're going to go ahead and move on then. So I'm going to start with a drawing. Do it this way. Yeah, this is fine. So imagine that we have a spacecraft, and I'm going to draw it as a cube. And then imagine that it has a camera. And we'll say that it also has some solar panels coming out the side. There you go. And let's say I'll pick, what color do I want to do here? Do green. It's got some spacecraft reference frame. Let's tidy that up a little bit. It's got some spacecraft reference frame that looks like this. And then we've also got some camera reference frame that looks like this. Down. And so let me ask this question, and I'll take a brave volunteer who thinks they can answer a question or would like to try to answer a question about spacecraft attitude. Any takers?
I'll try.
All right. So this is actually going to be, well, we'll see. We'll see what you think about this question. So what is the orientation or the attitude of this spacecraft?
Well, like relative to what?
Yeah, see, that was it. That was the right answer. Thank you.
Oh.
That was exactly right. I'll mention here that this is the spacecraft body frame, and then this is the camera frame. So you might remember, I think it was John DeLuca that mentioned that last time. I said, where is the spacecraft? And he said, in reference to what? And like that was exactly what I was looking for. So there we go. This is the camera frame. This is the spacecraft body frame. And Natalia very adeptly said, in reference to what? So I'm going to write that down. Here's a couple of questions we could ask. Which way is the camera facing? Or what is the spacecraft's attitude? or the attitude of the camera? And the right question to say is in reference to what? All right. So I'm going to ask the same question. And Italia, you're off the hook. You've answered one. I'll take a different brave volunteer. Let's just say for kicks that we've got a world frame. Maybe we could use the International Celestial Reference Frame. Call this ICRF. Okay. So now, anybody who's feeling brave, how would you express the orientation or the attitude of the camera with respect to the International Celestial Reference Frame? Clearly, they're not lined up. Clearly, they have different orientations. What's the difference? Like, what's the relationship between the two? Any ideas?
You're able to do it with three separate rotations, right?
Ah, you're way ahead of me, Corey. Very good, very good. So the three separate rotations is something we're going to be talking about. Um, bear with me. In 5 pages worth of notes. So you're way ahead of me. That's excellent. So what I'm trying to say, and this is my main point for this kind of introductory question, is when we speak, is we're really speaking of a 3D rotation from some frame, which is typically inertial, to some other frame, typically, let me just, here we go, typically fixed in the spacecraft. There we go. Or it could be in the instrument or whatever else it is, right? So what we're talking about is the International Celestial Reference Frame and the camera they have two different reference frames that are related by a rotation. So when we want to say, it's the same thing. If you want to say the position of a spacecraft, it has to be in reference to something. It has to be this many, kilometers in this direction expressed in the Earth-centered inertial reference frame, right? So you need a reference frame. Similarly, with attitudes, you also need a reference frame. So that is to say, here's what we would need to do to the ICRF frame to make it look like the camera frame. And that rotation is what we're going to be talking about today. So questions on that? I have a couple of high-level ideas, and then we're going to get into specific ways of implementing that. But so far, so good? Now, there's one point that I want to make before we go on super far, which is this, and this is important. It's a little start. The robotics community, especially those of you that have taken robotics might know this already. The robotics community typically uses active rotations. And what that is to say is you're taking a vector and you're moving it, moving a vector. So you can imagine the vector describing the position of the end effector of some robotic arm. When we rotate it, when we express that rotation, we're expressing the literal motion of a vector in 3D space, right? So that position of the object is moving, you are moving the real item, okay? The navigation community, or we're just gonna say the GNC community, typically uses passive rotations. And so the difference is what we're really doing is we're moving the frame. So if I said, okay, here's the spacecraft position expressed in the Earth-centered inertial reference frame. Find me the spacecraft's position in the Earth-centered Earth-fixed reference frame. What we would then need to do is find the relationship between the Earth-centered inertial and the Earth-centered Earth-fixed reference frame and do a passive rotation between those. But what we're not doing is physically moving the spacecraft. At that instant in time, the spacecraft just is where it is, and we're expressing it a new way. So another way of thinking about passive rotations is expressing the same vector in a new way. And so this is why it is my pet peeve when people say, I'm going to describe the attitude of this spacecraft with a rotation matrix. No, you won't, because a rotation matrix describes the motion of an object in space. An attitude transformation matrix describes the relationship between one frame and another. And you might say, same difference, why don't you just push up the glasses on the bridge of your nose and say, well, actually, but there really is a difference. It's actually a critical difference. They are inverses of one another. So if you code up the wrong thing in your flight software, you will crash. And it's very important that people know the difference. So we'll get into more detail on this in a little bit, but it's important to know that mathematically, active and passive rotations are inverses of one another. There we go. So we're going to talk about that in greater depth later, but if you're like me, you learned how to put together a direction cosine matrix, and then later you took robotics and you saw how to put together a rotation matrix, and you saw that they were different, and it made you very confused. And so I'm here to say this is why, right? So we'll go into some detail about the differences, but for now, a very quick way to get me to correct you is to use the word rotation matrix when you mean direction cosine matrix or attitude transformation matrix. Is not the same thing. All right, another quick aside before we get into this. Quick aside is degrees of freedom. I always love to talk about degrees of freedom. I think it's a good thing to consider. Matter of fact, if any of you have taken a controls class with Dr. Joshua Hurst, he won't even start to solve a problem until he knows that he has the right number of equations and right number of unknowns. And so he gets you to start thinking about the degrees of freedom of a system and whether you have enough data to actually say anything about it. I think that's a great practice to get into. So we're going to try to do that with some frequency in class here. So the degrees of freedom. How many degrees of freedom? And whoever wants easy points, we actually already asked about this. I think it was on the first day, or might have been the second day. How many degrees of freedom, DOF, does a 3D attitude have? So that's a softball. Whoever wants to key in their mic can answer that one. Oh, are y'all having a moment here?
I mean,
Is
would
it?
would it
Folks
just
need
be
to jog their
three?
memory on this one.
Oh,
Oh, what'd you get?
Would it just be like 3 with a roll pitch yaw?
Oh, sorry, Mary. I can hear that you're saying something, but maybe my volume is set too low.
Would it just be 3 for like a roll pitch and yaw?
That's exactly it. Yes, thank you very much. Very, very good. So that was the next thing I was going to make the point. In 2D, you can kind of just imagine in 2D, attitude has only 1 degree of freedom. You can just think about it. If you have some object, you can just rotate it this way, or you can rotate it this way. That's all there is, right? There's only 1 degree of freedom. In 3D, attitude has 3 DOF. Very good, Merritt. And so one way you could think of that, you actually already jumped to it, is roll, pitch, and yaw, and we will talk about that today. Another way you could think about this is an azimuth and an elevation angle to describe your pointing vector. That's two numbers. And then a clocking angle to describe remaining degree of freedom. What we're going to say is basically there are three numbers that you need to know to describe the attitude of a spacecraft. And you kind of have your choice. Roll, pitch, and yaw are not the same thing as azimuth, elevation, clocking angle, and it's also not the same thing as an angle vector, and it's also not the same thing as the 3 degrees of freedom in an attitude transformation matrix, and it's also not the same thing as the 3 degrees of freedom in a unit quaternion. We're going to talk about all of those either today or next class. But the point is there are 3 degrees of freedom. And so when we talk about different ways of expressing attitude, they're all just different methods of capturing those same 3 degrees of freedom. It's like you can say, you know, hello, my name is Paul in any language that you want. It's the same content. We're just expressing it different ways, right? That's essentially the idea. And so what we're going to cover either today or next class, because I have 9 pages worth of notes, and I think it usually takes about an hour and a half to go through 6 pages worth of notes. So we're probably going to need to split this content up over 2 days. But we are going to discuss in this class, we will discuss attitude transformation matrices, also called direction cosine matrices. Euler angles, angle vectors, and quaternions. And we'll talk about how to map between all of those. So if you know the angle vector, you can also find the attitude transformation matrix, and you can also find the quaternion. Same idea. Okay, great. So next is attitude transformation matrices, but this is a great natural stopping point. Any questions? We all doing okay so far? All right. All right. So attitude transformation matrices are one of the most common ways in linear algebra to express a rotation. One of the most common ways. This is going to be kind of a wordy lecture here, so bear with me. One of the most common ways in linear algebra to express a rotation. It is also called a direction cosine matrix. And then not the same thing as a rotation matrix. There we go. An attitude transformation matrix is, in 3D space, an attitude transformation matrix is a 3 by 3 orthonormal matrix. So what does that mean? It means that each row is a unit vector, each column is a unit vector, and each row is perpendicular to each other row. So essentially you have one vector describing some direction, and it's a unit vector, another vector describing an orthogonal direction, that's a right angle, and then a third direction, which is a right angle to both of the other two. And I mean, that's That's the right-handed rule, right? That's this. So you've got direction, 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 all with a length of 1 and all mutually orthogonal to one another. And that's what a attitude transformation matrix gives us. And so you might see this written as being a member of what's called the special orthogonal group. Special orthogonal group 3, which is sometimes written as SO3. So you might see a matrix T is a member of special orthogonal group 3 written in some fancy paper somewhere. That's what they're saying, right? T is a member of SO3 means it's a attitude transformation matrix. We know that every row and every column is a unit vector. And another very useful property, which is something we're going to want to remember here, useful property, its inverse equals its transpose. So if you have an attitude transformation matrix, so if I wanted to do something like this, actually here, rather than jump the gun, let's just go right to this. We will use this notation. We will use the notation that an attitude transformation matrix which takes a vector from the A frame to the B frame is written like this. T for transformation, A is the before and B is the after. So this is before, and this is after. And the way that I like to think about it is it's a little bit like gravity, right? So like A falls onto B, right? That sort of thing. So those of you that have taken classes from Dr. Kurt Anderson would have seen this written as C from A to B. It's the same idea, right? So his notation maps this way, and he uses the letter C for cosine, as in direction cosine matrix. I prefer this notation. It's the same idea, right? Same basic idea. All right. It occurs to me that I might have put the cart before the horse a little bit because we did some attitude transformation matrix work last lecture in the discussion of orbit elements. So y'all have seen this once before, but hopefully now it makes a little bit more sense. So we can say this. So we can say that if you have some vector P expressed in the A frame, and you multiply it by a matrix, which takes you from the A frame to the B frame, you're going to end up with some matrix P expressed in the B frame. But, and this is crucial, it's the same vector. P did not move, we're just describing it something differently. And that's what makes this a passive rotation, where P is a 3 by 1 vector. Very good. So let's do an example. Simple rotation about the z-axis. So some of you have seen this before. Some of you are kind of snoring at this moment because you've seen this a bunch. Rotating about the z-axis to get an attitude transformation matrix is one of the first exercises that you learn. I still think it's good just to do this as a refresher, and there might be some of y'all who are seeing this mostly for the first time. So it's important to go through and be very thorough. So here's our example, simple rotation about the z-axis. Consider a vector P that can be expressed in the E frame or the U frame. go. And so we'll say this. We could say P expressed in E is going to be PE1 times the E1 direction plus PE2 times the E2 direction plus PE3 times the E3 direction. Or if you wanted to, you could express it in the U direction. So this would be PU1 U1 plus PU2 U2 plus PU3 U3. And so the critical thing here is that PE1 does not necessarily equal PU1. PE2 does not necessarily equal PU2. PE3 does not necessarily equal PU3, but it is the same vector. Okay. Oh, and I should mention, just in case it wasn't already clear, any vector like this, like if I have the letter A and then I put a hat on it, that means it is a unit vector. Its norm equals 1. So that's just kind of a quick aside. Okay, so let's do a quick example then. Suppose the frames are related as follows. And we're going to need a volunteer real soon, so start working up the courage to answer a question here. All right, let's say we've got some frame, looks like this. So you've got E1, E2, E3 is coming out of the screen at you. And then let's switch to, kind of feeling green today. We've also got some U1 and some U2. And then U3 is also coming out the screen at you. So it didn't move. E3 and U3 is the same direction. And let's say that the angle here is theta. So you can imagine that the difference between the E frame and the U frame is a rotation theta about the Z axis, which they both share, right? Okay, so we could say this. The E frame and the U frame are related by a simple rotation about the third axis or the Z axis. And it's kind of either, right? Because they share it. Okay, great. So this is where it's going to start to get a little bit fun. Somebody who's seen this before, this is going to be real easy here. Maybe I'll do this in green. What is the U1 basis vector in terms of E1, E2, and E3? And then we're going to do it here. All right, I'll take a volunteer or we can roll the dice depending on what you're feeling.
I can go.
I got someone?
Yeah. Can you hear
Okay,
me?
sorry, I didn't hear you. Hi, Renee. So it's the air conditioning unit I have on behind me. It's making it hard to hear y'all. All right, so easy one. Ooh, actually, whichever one you'd like to do. Do you want to do U1, U2, or U3?
U1, sure.
Sure, what's U1?
So in the E1, it's cosine theta E1 hat plus sine theta E2 hat.
Very good. And so that comes, and I'm actually going to do this. I'm also going to say that it's 0 in the E3 direction.
Fair.
Which is kind of, I mean, you could, yeah, it seems kind of academic to do it that way, but it's going to help us build the matrix in a minute, if you can see that. So great. So to take U1 and map it onto E1 is the cosine operation, and to map it onto E2 is the sine operation. Do you want to keep going or you want to pass off to somebody else?
I can keep going.
All right, you got some gas in the tank? Let's do it.
Sure. And then U2 is minus sine theta in the E1 direction and plus cosine theta in the E2 direction.
Good. And then also going to
And
be
0 in the
yeah.
E3.
And now the hardest one of all, U3.
1 E3.
There you go. We have to write this to be thorough. So there we go. 0 E1 plus 0 E2 plus 1 E3, or in matrix form, we could think of it this way. Here's what this is saying. And thank you, Renee. Very good. This is saying that U1, U2, U3 is related to E1, E2, E3 by the matrix cosine of theta, sine of theta, 0, negative sine of theta, cosine theta, 0, 0, 0, 1. Those of you that have taken robotics might be wondering why there isn't a minus sign right here instead of right here. And that is a rotation matrix. If you have a negative sign on top, it's a rotation matrix, because that is the same thing as the transpose of this matrix, which is the same as the inverse of this matrix. So that, for me, that really made my eyebrows go up when I was taking robotics and I saw the minus sign move. But that's the idea. So this right here is T, which maps from E onto U. All right. Thanks again, Renee. And so what this means is, for everybody, that, and this is crucial, an attitude transformation matrix is just a list of basis vectors. Because that's all we did. We wrote U in terms of E, and those three basis vectors stacked gives us T from E to U. And so also, this is kind of, pretty straightforward from what we've already talked about. So we literally can say, all right, P expressed in E is just P expressed in U after it's been mapped over by this attitude transformation matrix. And we can also say that T from U to E, which we don't know, we have T from E to U. Well, that's the same thing as the inverse from T, U to E, which is the same thing as the transpose. And if you're looking at a matrix like this, you just move the minus sign. That's all it is, right? So interestingly enough, the attitude transformation matrix that maps from U to E is the same as the rotation matrix that maps from E to U. So it's kind of just very important to get that straight. I'm going to say that like 50 times today. These are not rotation matrices. These are attitude transformation matrices. Okay, great. So I think that's a good pausing point. Any questions on that so far? Otherwise, we have a more involved example coming up, and I'll need an even braver volunteer in a minute. But we good? Questions so far? All right, I'm going to keep on moving. So this is an example that I use at work. So that something like this is like not necessarily day to day, but it does come up with some frequency. Is building. Oh, I guess this is an example. Start with that. Example. Building a local vertical local horizontal, or LVLH frame. So suppose a spacecraft is in low Martian orbit. Okay. And it has a sensor pointed along its z-axis. Okay. And that sensor that needs to be pointed straight down You might be familiar that the aerospace word for straight down is nadir. And then pointed straight up would be zenith, right? Same idea. So zenith pointing, nadir pointing. So this is one kind of point here. It is also desired that the spacecraft x-axis be pointed prograde, which means in the direction of motion, as much as possible. Because you might be saying, what if straight down and in the direction of motion are not at right angles to each other? So we're just going to do our best with the spacecraft x-axis, but the spacecraft z-axis really needs to be pointed straight down. So what I'm going to do is I'm going to challenge us and some brave volunteer slash victim. We can construct, and I'm getting really tired of writing attitude transformation matrix, so I'm going to say an at transmat, just to save on keystrokes here, from the MCMF frame to the LVLH frame using the spacecraft position and velocity expressed in MCMF. That is our challenge. And if that doesn't immediately make sense because of my words, it's going to make a lot more sense in a second because of some pictures. But really quick, I'll take anybody who feels like just keying in their microphone. MCMF, what does MCMF stand for again?
That's Mars-centered, Mars fixed frame, correct?
I'm impressed because I said MCMF stands for moon-centered, moon-fixed. So you didn't fall for the trick. I'm impressed. Very good. It is in a Martian orbit. So MCMF, in this case, because of context, is Mars-centered, Mars-fixed frame. Now there's, you might call it like an areocentric, I forget what the proper term is for it, but we're just going to use MCMF for now. You get the idea. So let's say that this is Mars. And let's say that there is a spacecraft with its camera. We're trying to point it straight down. And you know me, I got to put solar panels on it. And it's in some orbit. And this is the MCMF frame. So we're going to call this maybe M X direction, M Y direction, M Z direction. And we know what? We know the position and we know the velocity. So we know this, and here's what we want. Yeah. Getting slightly better at drawing circles. Oh, maybe not. There we go. And we want the spacecraft to have, maybe I'll use blue for this. Like a lighter shade of blue. We want it to be pointed in, so we'll call this the EZ direction, and then the EX direction is pointed in the direction of motion as much as possible, and then the EY direction completes the right-handed system. All right, and so we'll call this the LVLH frame. And then in this case, we'll go back to red for a second. All right, and this is the MCMF frame. So we're actually going to build an attitude transformation matrix from one to the other. We're going to do it one vector at a time. All right, so this is where you need a volunteer, and this next part's going to be maybe a tiny bit tricky, but we're going to work on it together. So somebody brave, we're going to build the the EZ direction, you and me as partners. So who's feeling brave? Y'all are gonna make me break out the dice today. All right, let's do it. Let's do it. I gotta pick a victim. We gotta make this interactive. Let's see. Do we have let's see. Nate Carwick, are you here today?
I am, but catch me for the next one. I'm actually sending you an email right now.
Oh, are you? Okay, cool. So maybe now's not the right time then, Nate. I'll try one more time. Let's see, let's see. That would be Corey. Corey, did you already answer something? I can't remember.
I think I've answered a couple small things, but
All right. Well, you've been called upon by the dice, it looks like. So we're gonna work on EZ together. And if you're feeling not 100% confident, even better, because this is a good learning experience. So you and me working together, the EZ direction is pointed from the spacecraft down at Mars. Okay. How would we write that in terms of math? Like EZ equals what?
it's gonna be. Er, is the R vector a unit vector, or is that?
No,
have-
it's not. It's
Okay.
not. That's a good, but let's start with that. Is the EZ direction the same as the R vector? Not exactly, but we're kind of on our way now, aren't we?
Yeah, then divided by the length of.
Yeah, divided by its own magnitude. All right, are we done, or is there one more step?
It's negative.
Very
Because
good.
it's pointing
Excellent.
the opposite direction.
Excellent. Very good. Good job, Corey. All right. The next one is a little bit trickier, so I'm going to do this one on my own, but then I'll get a volunteer for the third one. So that's the plan. All right. Good job, Corey. So to find EX, remember, we want EX to be pointed in the prograde direction, meaning along the velocity vector, as much as possible. R and V do not have to be at right angles to each other. So what we're going to do is we're going to find the projection of the V vector onto the plane perpendicular to the R vector, if that makes sense. So V could be in any direction, but we want the projection of V onto the plane perpendicular to R. And we're going to show how to do that mathematically. So to find EX, we want the projection of the velocity vector onto the plane, I'm running out of space, perpendicular to the position vector. Okay, so the way we're going to accomplish that is first find the component of V that is along the R direction or along the EZ direction. Okay, so the way that we would do that is we would say, okay, the EZ vector transposed onto velocity, or velocity transposed onto EZ. This is essentially the dot product, right? The dot product of the EZ direction and the V vector gives us the component of velocity that is along the radius from the center of Mars to the spacecraft. So this is essentially the radial velocity. But this is going to give us a scalar. So all of this, we need to kind of remember, oh, this is in the EZ direction. Okay, so you see EZ twice. The first is saying the projection of V onto EZ. That gives you a scalar, but that scalar is in the EZ direction. This is essentially what we want. This is the same thing, if we're comfortable with our vector math, as saying EZ transpose V. Same thing. All we're doing is moving a scalar from the beginning to the end. But kind of by the law, the commutative property, right? We can say, oh, actually, or I guess the associative, I'm trying to remember which is which. EZ transpose V is the exact same thing. Okay. So if we scroll down a bit, and I think OneNote is being a bit annoying, so we might need to save and restart at some point. But anyway, this is not what we want, right? This is the component of V that is along the radial direction. We want the rest of V, right? So what remains of the velocity vector must be the part that is perpendicular. So we want the remainder Or in other words, the part of V which is perpendicular to EZ. This is the projection of V onto EZ. This is the opposite. And so we're going to define some vector U. I don't think we're using U right now. U is velocity minus EZ transpose V. Or if we're going to do a little bit of grouping, the identity matrix I 3 by 3 minus EZ transpose V. And so what all of this does, and this is important to remember, identity matrix minus vector transpose is a matrix. It's going to be a 3 by 3 matrix which projects V onto the direction perpendicular to EZ, right? And so that still doesn't answer our question, right? We're still not quite there yet because we don't want U, we want EX. And you might say, okay, U equals EX. It's like, au contraire, it does not. We have not made it a unit vector. So in a second, I'm trying to get the eraser tool working here. Yeah, we could be very close to restarting OneNote. Matter of fact, I think once we're done with this example, we'll take a 5-minute break and then I'll restart OneNote because it's getting a little, it's not cooperating. Velocity projected onto the plane perpendicular to EZ gives us some intermediate vector U. We normalize that to find EX. Okay. Finally, we get to another one which I can do with a partner. So I'll take a volunteer who hasn't gone yet today, or we can consult the dice and see who they
I can do it since I skipped the first one.
Okay, perfect, Nate. So this one's going to be a little bit easier, and I appreciate you coming back around. That's good. Finally, we need EY. So remember, EZ is just the position vector negative normalized. EX is the hard one, and that is velocity projected onto the plane perpendicular to position and then normalized. What is EY?
Should be X cross Z. No, Z cross X.
Ah, very good. EZ crossed with EX. So we can just say the Y direction completes the right-handed system. So one of your vectors is always a freebie. It's like a bingo free square, right? If you do the hard work of finding 2 of them, the third one is just cross product of the others. And I like to think about it this way, right? X crossed with Y gives you Z. Z crossed with X gives you Y, and Y crossed with Z gives you X. So I like to write that in the margin of my paper if I'm going to be doing a lot of cross products. Now, even after all that, we're still not done. There's even one more step. I guess I used the word finally prematurely. Now we can construct the matrix T from the Mars-centered Mars-fixed frame to the LVLH frame is EX transpose, EY transpose, EZ transpose. So you can think of these as being wide vectors rather than tall vectors. And I'm going to try one more time to draw a straight line here. Sorry, here, bear with me. Okay, good. So Control Z is not working and the eraser is not working. So that's actually a perfect time for a break. So why don't we come back at, so let's see, it's 5:50 for me, 6:50 for you. Why don't we come back at 6:55? And I'll stick around in case anybody has any questions during the break.
I had a question about the homework.
Are you able to save that until after lecture, or do you think it's going to be a real quick one?
It was just, I might be a quick thing because it was about downloading the Spice stuff because I downloaded it, but it says error and C Spice Furnish. I don't know what that means because I downloaded the files you said and put them all in like the same directory. Did
Okay, good. Good. So far, so good then. And then it didn't like that though?
no, it still won't run.
Hmm. So there's the spice files, like the mice files, the MATLAB spice. And
Yeah,
then there's also the kernel files, right? There should be a SPK file and an LSK file, right? Spice kernel and leap second kernel file.
yeah.
Are those also within like arm's length? Like are those in the correct directory or are those somewhere else?
I put them in well, I downloaded all that stuff like the mice thing and the separate kernels they said to do, but I put the kernels in the mice folder.
Oh, it might not like that. It might not
Oh,
like. I think what matters is there's a line where you say C Spice furnish because that's what furnish is short for furnish. You're trying to furnish it with the information, and then you point it to a directory. If your leap second kernel and your Spice kernel files aren't at that address, it's going to throw an error. So I think that's a good sanity check is to make sure that the address that you have in your argument is actually pointing to like where they go because you can save them wherever you want. But the example file that I made won't run out of the box unless you're careful to make sure you're pointed to the right directories.
okay.
Yeah,
So,
so just play around with those commands and see what that does for you.
okay, thanks.
Absolutely. And if you get hopelessly stuck on that, obviously it might be easier to chat with somebody else who's like also kind of elbows deep in it, but I can take a quick look at your code for you if you get hopelessly stuck.
Hey Paul, good question.
Yeah, what can I do for you, Calvin?
I'm just the I 3 by 3. That's just the identity matrix, right?
Yep, I should probably mention that. This is
Okay.
the identity matrix.
All right. Thank you so much.
Yep. It's the equivalent of the number 1 in matrix land. 1 0 0 0 1 0 0 0 1. There we go. Great. And I'll at least start the next thing, but we won't talk about it yet. All right, I think it might be time to start back up again. It's 5:55 for me, 6:55 for you. So we'll start off slow here and then we'll kind of ramp back up to speed. All right, so next we're going to go into more detail about that thing that I was kind of whining about earlier, which is the active and passive rotations. So an active rotation is the inverse of a passive rotation. and vice versa. So we're going to illustrate this. In 3D. And this diagram that I'm about to draw is what made it click for me, so I hope it helps for you as well. So we're going to start by partitioning our diagram space here, and we're going to use plenty of space. And on the left, we're going to do a passive rotation, and on the right, we're going to do an active rotation. Okay, this is going to get a little bit busy, so I'm going to try to draw this big. There we go. Probably do for now. So we have E1, E2, and then I guess E3 is coming out of the page. And then I go to green, feeling green today. We have, this is the same diagram as before here, U1, U2, and U3 is the same as E3. Right. And we're going to say that these are related by some rotation theta. And I'm not going to write theta down here. Do we have room for it? Maybe. I'll try to squeeze it in there. Theta. Okay. And let's say then that we've got some vector, which is right here. And we're going to call this vector P. Right. And what I'm going to do is I'm going to project P down onto the E direction, and I'm going to call that number A. And I'm also going to project P onto the, the E1 direction. The E2 direction projected is going to give us B. But I'm also going to project P onto the U1 direction, and that's going to give us alpha. And I'm going to project P onto the U2 direction. We're going to pretend that's a straight line, and that's going to give us beta. Okay, so here's what I'm really saying. Oops, hang on, let's get rid of that last stray mark there. Here's what I'm really saying. That PE, okay, is AE1. I'm going to scroll down just one more click of the mouse wheel here. Plus BE2 plus 0 E3. PU is alpha U1, which we can see visually that alpha and A are different numbers, plus beta U2 plus 0 U3. And actually, we know, here, I'm going to scroll up again in a minute here, so just bear with me. PU is the same thing as PE. We know that. We can see there is no such thing as PU or PE. There's only P and the way we choose to express it. And we can map between those expressions using this matrix. This should feel like deja vu because we've already talked about all this. And we also know from our previous discussion that the matrix which maps from the E frame to the U frame looks like cosine of theta, sine of theta, 0, negative sine of theta, cosine theta, 0, 0, 0, 1. None of this is news, right? This is basically the same thing that we had a second ago. Okay, so then bear with me if you don't have that written down. We're going back to it in a minute. Now we're going to look at an active rotation instead. And so this is one where the P vector literally moves. So we're going to work only in the E frame here, E1 and E2. Okay. And so let's say that we have this exact same vector P. And maybe I will write P up here. Actually, maybe it makes more sense to have P written up here as well. So there's the P vector. It's the same P vector. I want to make that very clear. And so what I mean by that then is if we were to project it onto the E2 direction, I'm going to try a little bit harder at drawing a straight line. I'm not that much of a perfectionist, but I can do a bit better than that. There we go. Projected onto the E1 direction gives us A. Projected onto the E2 direction gives us B. Then let's say instead that we wanted to rotate P, and maybe I'll use red for this. Here's P prime, where the relationship between P and P prime is some rotation theta, but critically, P prime is in the opposite direction. Okay, so now what we're going to do is we're going to project onto this direction, and it gives us beta, and project onto this direction, and it gives us alpha. And so what we're saying here is this. P, expressed in E, is A E1 plus B E2 plus 0 E3. So P E prime, this is a different vector, very critical, different vector, is alpha E1 plus beta E2 plus 0 E3. And so the way we would write this is P E prime is rotation about E3, some amount negative theta times PE. This is our notation here. So the big R, which we're pretty much only going to see in this lecture because this is not coming up again. Rotation about E3, so that's the axis. So just make this clear here. Rotation, axis, angle. But clearly we can see that the rotation matrix that maps from P to P prime has to be the same as the attitude transformation matrix that maps from PE to PU, because PE prime is PU. It's alpha and then beta and then 0. And so what that means then is we can say this. This actually works out to be the cosine of negative theta and then the negative sine of negative theta, and then 0, and then the sine of negative theta, and then we have the cosine of negative theta, and then 0, and then 0, 0, 1. But that's just the same thing. Cosine of theta is the same thing as cosine of negative theta. Negative sine of negative theta is just sine of theta. Sine of negative theta is the same thing as negative sine of theta, and cosine of negative theta is the same as cosine of theta. And so what happens is they're the same thing. So the rotation matrix, which describes, I'm going to say the same. The rotation matrix that describes a negative theta rotation is the same as the attitude transformation matrix that describes a positive theta rotation. So that's my way of kind of getting the idea across that these are expressing opposite things, but they're the same. Or if we wanted to say rotate theta about E or make an attitude transformation matrix theta about E, then what we would get would be the transpose or the inverse of one another. So an attitude transformation matrix equals the rotation matrix describing the opposite operation. All right. So for those of you that are tired of hearing me trash talk rotation matrices, we have officially ended that phase of the lecture. We're going to move on to other stuff now. But I've had people at NASA ask me, what is a rotation matrix? I thought that's the same thing as a direction cosine matrix. And it's like that can't happen. So, I mean, most people know, but it's important that everybody knows, especially if you're writing flight software, that sort of thing. Anyway, so questions about rotation matrices, or do we think we're okay to move on to the next topic, which is 3-parameter and 4-parameter representations? Cool stuff. All right, moving on. 3 and 4 parameter attitude representations. I think we'll make it through roll, pitch, and yaw today, and I think that's probably be where we'll stop. And we're going to split this content up over 2 lectures because this is very important, and we don't want to skip out on any of this. But I think it's going to take a little bit longer than I'd originally considered. So remember that attitude transformation matrices are orthonormal, okay? Which means what? It is a 3 by 3 matrix, okay? But we have perpendicular basis vectors, okay? And we have each row and each column is a unit vector. So let's go back to discussing degrees of freedom, right? So there's a 3 by 3 rotation matrix. That means we have 9 numbers. And how many constraints? Because remember, the number of equations minus the number of constraints equals the number of degrees of freedom. You might have learned that in a dynamics class, right? 9 numbers, 3 by 3 matrix, but we have 6 constraints. Each row is a unit vector, that's 3 constraints. Each column is a unit vector, that's 3 more constraints. So 9 numbers and 6 constraints leaves us with 3 degrees of freedom. So then that kind of leads to a question. Why don't we just use 3 numbers instead of 9 numbers, right? Why do we bother with 9 numbers? And actually, depending on what you're going to be doing, it makes little sense. So it makes little sense to store 9 numbers in a very data limited flight computer where every byte matters when only 3 are necessary. So in the words of Kevin from The Office, why use 9 numbers when 3 do trick, right? So that's going to be what we discuss next, is different ways of expressing attitude with 3 numbers instead of 9 numbers. So the following sections describe other ways of expressing attitude. And how each is converted back into an attitude transformation matrix. So we're going to talk about Euler angles today, and then we're probably going to stop maybe about 20 or 25 minutes after the hour, and then we'll break. And then next time we're going to talk about angle vectors, Euler axis, Euler angle, and unit quaternion. So there we are. We're going to discuss Euler angles. Questions before we move on? Everybody's feeling okay? So, Merritt, you mentioned roll, pitch, and yaw earlier. I'm going to ask you in a minute to label roll, pitch, and yaw on an aircraft. I hope you're comfortable with that. If not, remember, you can always just tell me no. I mean, I can't. What am I going to do?
Yeah, that sounds good.
All right, cool. We're going to talk about that in a minute. So, Euler angles. This is an important point. And who was it? Oh, okay. This is my short-term memory. Somebody said earlier It's going to sound real familiar. Any rotation can be expressed as a product of 3 rotations about axes fixed in a body or fixed in space. So who was it that said that? Somebody earlier? Come
I
and
think that
take
was
your
me, sort of.
Mhm.
A little less
I think it might have
eloquently
been.
at any rate.
It might have been. I mean, so you get some credit, but I think it's really this guy, like Euler. Euler said it first, but you were absolutely right. That yes. So when I talked about describing the attitude of a spacecraft, oh, hang on. Okay, well, this is just going to be fine. All the way up at the top of the notes today, I said, what's the relationship between the ICRF frame and the camera frame? You said 3 rotations. And so that's basically what we're talking about now, is you can use 3 rotations to get from A to B. Okay. There we go. So in this class, and in spacecraft navigation in general, and this is another important point, just the same fuss that I made about rotation matrices versus direction cosine matrices, you could make the same fuss about body rotations and space rotations. I'm not going to make that fuss, but it's worth mentioning that space rotations are when you rotate about a direction, but that direction doesn't move, right? You rotate about the world frame, and then you rotate about the world frame again, and then you rotate about the world frame again. That sort of thing is often done by computer programmers, and specifically people that make video games or animators or anybody that works in 3D graphics and rendering will typically use space rotations, because if you have an object, if you just have a cube, right? The cube, those of you that have ever worked with Blender, you start with a cube. Like, you can rotate about the world x-axis, the world y-axis, and the world z-axis until your heart's content, right? So it makes sense in the computer, you know, the rendering software, Pixar, animation, video games, all that stuff. If you have a friend who has a GSAS major, same idea. Whereas if you have an aircraft, and here's Paul's fighter aircraft. There you go. That's a fighter aircraft. It can only rotate about its axis. It can do a roll, a pitch, or a yaw, because those are where it actually has control surfaces, right? So it actually kind of matters. You're rotating about axes that are themselves rotating, and that would be body fixed versus space fixed. So I think while I'm not necessarily going to write that out or talk about it for like 45 minutes, it's important to know that there is a difference, and that might also be a cause for confusion if any of you have a background in video games, graphics, or rendering. So we'll talk about that in a minute here. So we will focus, go away please, there we go. In this class, we will focus on body rotations, because a spacecraft can use thrusters or reaction wheels, what have you, to rotate about its x-axis, not some world x-axis. So if you're into video game design and you have a cube, you can play God and you can just reach out and rotate it any which way you want. But a spacecraft only has control authority along certain principal directions, right? So that's why we're going to be talking about body direction. So a rotation, and Merritt, it's about time for you to take the stage about the body. That's a Y. The body x-axis is often called What is that, Merritt?
Would that just be the one going in like the same velocity or in the velocity direction?
Oh, you know what?
Yeah, because I know it off of
I
like if
should
I
have
have a
drawn a-
picture of
let me
something.
start with the picture. Yeah. No, I
Yeah.
put the cart before the horse. Okay, let me start with the picture. Get ready. This is me drawing a Cessna 172. Okay, get ready. So it's got a little nose, a little cabin. It's got a wing, big old wing. This is going to turn out all right, I promise. All right. And then it comes down here, and it's got a vertical stabilizer. It's got an elevator, just like that. This comes down this way. The whole thing looks like this, and there's a person inside having a grand old time. It's got some struts supporting the wing. It's got, for bonus points, what are the control surfaces right there called, Merritt?
Those
That's a bonus
ones.
question. Sorry, I interrupted you.
I forgot what those ones.
That's all right. This is a more of an aero, like pure aeronautical question. Don't look at the perspective of this drawing. I promise it's correct. And then we got a little propeller out front right here. And maybe the propeller has like a little nose cone. It's going real fast. So this is totally off the beaten path and bonus, but what are the different control surfaces called? I'm just curious if anybody knows.
That's the ailerons, and then the elevators are on the tail with the rudder on the vertical stabilizer.
So we have so the rudder is going to be this guy. The elevators are here and they kind of control this rotation. This one controls this rotation. And then this way it controls, well, this is going to make a lot more sense in a second here. Very good, Kevin. And so that's more of an arrow thing. If any of y'all ever think about getting your pilot's license, if any of y'all are arrows and you think about heading down that path, you will certainly learn that in ground school. I actually took the ground school class that was through the RPI flying club, and I really recommend it. I thought it was very good. So I took that class in February and March of 2020, and then something happened, and all of a sudden I couldn't fly airplanes. So I didn't go through and get my license just yet, but I've at least taken the ground school and passed that. So it's really interesting the way they do navigations on aircraft. Actually, it's very cool. I could go off on a huge tangent about that if you want to. So Merritt, prime time. Let's do it. One of these is roll. One of these is pitch. One of these is yaw.
The rotation for on the x-axis, that one's roll.
Good.
Pitch would be the y, and then yaw would be z.
Pitch and yaw. Yep, very good. And it's really obvious on an aircraft. You can just kind of imagine when you're taking off, the captain will pull back and you'll pitch up, and that's actually how you get off the ground. And then yaw is actually something you kind of want to avoid on most aircraft. It's rough on the structure, and that is not how we turn. What we do instead is we roll and then pitch. And actually, that's kind of the same idea. You're accomplishing the same thing as a yaw by doing a roll and then a pitch. And then you use yaw to kind of keep your slip coordinate. You have to make sure that you don't let the tail kind of fishtail out while you're trying to fly in a certain direction. I digress. That's plenty about that for now. I'm going to just click and drag and move this down a little bit because that was not very thoughtful of me. Oh, hang on. We just like move. Yeah. I realize I want a little bit more space. There we go. See, that's nice, and you can't do that on paper. So a rotation about the body y-axis. Oh, I skipped this one. And that word is often. Looks the same as when I write the word after. X-axis is roll, y-axis is pitch. And finally, z-axis is yaw. There we go. Okay. And we got just a little bit more to go. If anybody has a schedule constraint and they need to take off, you're certainly free to go. I'm going to try to get through a few more lines, so it might take us until 25 or even 30 minutes after the hour, but then y'all will be dismissed. So if and I think it was Max who asked me this last class, or it might have been after class. So Max, you're going to be in the spotlight in a second here. If you choose to express a rotation as a yaw, then pitch, then roll, that is a what type of rotation sequence, Max?
So a yaw pitch roll would be a ZYX rotation.
Very good. So any of y'all that might have read ZYX rotation, or alternatively a 3-2-1 rotation, that's what that is. It's a yaw and then pitch and then roll. And now don't turn off your microphone just yet, Max, because I got to bug you a second time. And good job on that, by the way. The orbit elements, omega I omega, which we talked about last class, are angles corresponding to a, what type of rotation was it, Max? Do you remember?
Was that a 3-1-3?
Good. 3-1-3, or alternatively a ZXZ rotation sequence from the inertial frame to the parafocal frame. So this is just kind of closing the loop on that. We actually already did this. This is why it's a bit tricky. I couldn't decide when I was designing this course whether to put orbital mechanics before attitude representation or vice versa, because they kind of reference one another. But I think now that we're on the other side of this, hopefully it all clicks. And good job on that, Max. Thank you very much. So one other crucial point to make here is this. A rotation about the x-axis will leave all points along the x-axis untouched. The new frame will have the same x-axis, and then same for y and z, which this is not news. This is actually exactly what we talked about before. If we scroll up a little bit, where was that? Yep. Here we have a rotation from the E frame to the U frame about the third axis. It leaves it the same, right? E3 is the same as U3. All right. And so what that means is this. If we have some rotation, which I'm going to kind of break my notation for a second here, I'm just going to call this Tx of theta, meaning you're rotating about the x direction some amount theta, but because we're using a T instead of an R, it is a passive attitude transformation matrix. So if you're rotating about the x frame, it's going to look like this: 1, 0, 0, 0, 0, cosine theta, sine theta, negative sine theta, cosine theta. And if you wanted to rotate about the y-axis some amount theta, it's going to look like this: cosine theta, 0, negative sine theta, 0, 1, 0, sine theta, 0, cosine theta. So you can see, if you're rotating about x, the top left element, which is the x-axis, is unchanged. If you're rotating about y, the second element, which is the middle element, which is the y-axis, is unchanged. And if you rotate about z, we've seen this before, then it is the z-axis that is unchanged. So we get cosine theta, sine theta, 0, negative sine theta, cosine theta, 0, 0, 0, 1. There we are. And then in this, my notation is s theta is equal to the sine of theta. And then cosine theta is equal to That's just me trying to save on keystrokes. Just like when you're taking what is it, organic chemistry, and you stop writing H's after a while. It's like it's going to be shorter this way. So to put this together, a yaw pitch roll sequence would look like, I'm just going to call this T, and this is a ZYX rotation, is, okay, T, T, T. First, we're rotating about Z, some theta 1. Then we're rotating about Y, some amount theta 2. Then we're rotating about X, some amount theta 3. And here I'm going to notice that we're going from the right to the left, right? We start with some vector, then we rotate it about Z, then we rotate it about Y, then we rotate it about X, right? And what I'm going to do here is multiply this out, and I'm going to say that this is C1, C2, where C1 is the cosine of theta 1, C2 is the cosine of theta 2. C1, S2, S3 minus C3, S1, S1, S3 plus C1, C3, S2. You do not need to write this down if you don't want to. This is just me showing you how ugly this gets in a real hurry. C2, S1, C1, C3 plus S1, S2, S3, C3, S1, S2 minus C1, S3, negative S2, C2, S3, C2, C3. So if you wanted to write it out by hand, this is what you would need to do to go from these three angles to get this attitude transformation matrix. What I will often do if I'm coding it is I will just build TZ, and then I'll build TY, and then I'll build TX, and then I'll multiply them. It's more operations, but it's just a little bit easier for me, and it's fine if we're just doing homework assignments in that lab. All right, and so, okay, that is 27 minutes after the hour. We are 5/9 of the way done. Oh, I'm sorry. I hate to do it to you. There's 3 more bullet points, then you're done. All right, so 6:30 and we're done. Oh, hang on. Oh man, even OneNote doesn't want to work anymore. I know we've gone over a lot today. We'll take a break in a second. A different rotation sequence. Come on. Oh wow, is it actually going to crash on me? Come on. A different. Wow. A different rotation sequence would result in, oops. Wow. It's like I have to erase, and I know I don't even have a prayer of being able to erase this. Oh, jeez. All right, yeah, I think this is my computer wanting to give up on me here too. There we go. A different rotation sequence would result in an entirely different matrix. There are 12 possible body rotation sequences and there's also 12 space sequences. And then we have to be careful here. If you use Euler angles, and then, for example, roll, pitch, and yaw are Euler angles, this 3 rotation sequence, be absolutely sure everyone on the project understands the sequence. So what I mean by that is, if you have a table somewhere and you're listing the attitude and you don't feel like writing out 9 numbers, you say, look, here's the roll, pitch, and the yaw to get from the ICRF frame to the spacecraft body frame. Everybody who accesses that data table needs to know that you meant yaw, then pitch, then roll. Because if you do roll, then pitch, then yaw, or pitch, then yaw, then roll, or any other combination, it's going to give you a different matrix at the end. So everybody needs to be on the same page about that. And then also beware the dreaded gimbal lock. And we will talk about that next time. That is a great natural stopping point, gimbal lock. And we can talk about what that is next lecture, or if anybody's dying to talk about it right now, you can. Otherwise, class is dismissed, and we can use the rest of our time to either answer questions about this content or talk about the homework. But yeah, thank you very much, everybody, and have a great evening.